Hello everyone, welcome to Understanding Physics, in which I'll try to guide you through understanding physics. So today, after we have already talked about relativity, we want to dive deeper into quantum mechanics. So pretty much what relativity tells you is that if you have high energy or high momentum systems, physics doesn't really work the same. But the same thing happens when you're discussing about quantum objects. If you have very small masses or very small energies, the physics behave differently as well. So this is what we'll be discussing throughout this entire discussion. So before we get started, please consider liking and subscribing, and also please check the notes in the description for the notes throughout this entire discussion. So let's get started by actually discussing about the quantum theory. So quantum theory literally means quanta, which is quantization. So this means that you could actually separate it into those very small pieces. So something like charges. Charges are quantized because you don't have any charge in which it is 1/3 of an electron, even though those things exist, like the spin-up quark and the spin-down quark. They all have their own charges, but there is a limit into how small you can separate an object. This thing also works for energy, for momentum, and etc. But the way that we observe this will be mostly from experimental data that we will observe from this point forward. So let's talk about blackbody radiation. Blackbody radiation. So there are three things that blackbody radiation needs to do. First, from our understanding of radiation, P was sigma A T to the power 4. So you can determine the power of a radiation or the heat transfer just by only depending it on the area as well as the time. And so if you have a constant area, that means it will only depend on the temperature. And second, the peak of the wavelength is actually proportional to the temperature. So and this doesn't really depend on material, not material. So the peak only depends on the lambda. So we need to find a model of this. So this is what you call as Wien's law. Wien's law. And so this lambda times t, this is 1 over t technically. Yeah, 1 over t, sorry, my bad. So lambda t here was able to be computed to be 2.898 millimeter Kelvin. Now, these values here are based on experimental facts, but we still haven't have a model to explain all of these things. So let's actually try to think of a model for us to discuss all of these properties. So let's say if you have a perfect black body in which it could absorb light very well and it could emit light very well as well. So one condition of this black body object is that at the boundary it needs to be the electric field needs to be 0. So this means that it will have like a boundary condition of like a string, something like this. So the boundary conditions of these waves would be L, which is the length from here to here, must equal to lambda over 2, which is half of the wavelength. Multiply that by n, where n is a integer. So you can figure out what the n is, or the number of modes. It's 2L over lambda. So if you take a very small particular value of n, what you would have is this is negative 2L over lambda squared. And by the way, this n here will later be related to the energy. So how many n's exist? So how many modes exist for a particular n? And this is a very interesting question. So for a three-dimensional system, you could have these you could have these points, which corresponds to all of the standing waves for each of the directions. And so if you take a sphere and let it intersect each of these points, it will correspond to the amount of modes for a particular n, which is the radius. So this is like trying to figure out the area of, trying to find the surface area of n. So the total number of modes that exist for a particular value of n will be 4 pi n squared dn. So this corresponds to the surface area, and then the dn corresponds to the additional small thickness. And then you divide this entire thing by 8 because you're only considering positive values of n. Now, because we know how many n's exist, that means that we could figure, because you know how many n exist for a particular lambda, you could just put all of the values in to obtain pi over 2 times 2l over lambda, everything squared, multiply this by negative 2l over lambda squared d lambda. Okay, because this is a positive value, we'll just be considering a positive value in here. So what we obtain from all of these computations is that this will later turn out to be 4 pi L cubed over lambda to the power 4. That's d lambda, which is the times the d lambda, or the very small width of your variance of your wavelength. And that's the number of modes. So now a very clever idea of figuring out the number of modes after this is that you could actually figure out the kinetic energy. So there are these n number of modes, and then assuming that each of these modes have a average kinetic energy of kT, you could state this to be 4 pi L cubed over lambda to the power 4 kT. But also, because it's traveling at 2 different directions, that means that you could multiply this by 2 again. So this will correspond to the one that's going to the positive direction and the one going in the negative direction. And this is the small e for a particular d lambda, for a particular wavelength. Now we could actually use this formulation to figure out what is the energy density for a particular wavelength. So this energy density over wavelength, and this turns out to be dE over d lambda divided by the volume, which is gonna result in 8 pi over lambda to the power 4 kT. And this is what we'll call as U. So from this U, we could determine the intensity, which is the flux over time times wavelength times the salt angle, which is 4 pi. So this will later resolve itself into, so the flux in here is gonna be the energy density over lambda, over the wavelength. And so the unit for the flux will multiply this by the speed of light over the 4 pi. This is the energy surface density. So the unit in here makes sense right now. So this value here is the 8 pi over lambda to the power 4 kT. And so this will result in 2c kT over lambda to the power 4. Now, if you want to figure out what's the radians, or the R, you just need to integrate that from 0 to pi over 2, and the integral from 0 to 2 pi of the I, times the cosine theta sine theta, d phi d theta. So this component here corresponds to the transformation of the, so So this intensity is pretty much towards only one certain solid angle, but if you sum it up towards all of the different solid angles, you need to have this multiplying coefficient. So what you obtain from doing this integral will give you 2 pi ck t over lambda to the power 4. Now the interesting part of this is that this function doesn't really have a peak. Instead, the function turns out to be something like this. And this is where there's something which you call as the UV catastrophe, in which there should supposed to be a peak at the UV range. But in here, it turns out that it's going max and then it's going higher and higher. So there's something that's missing. And so the experimental data gives you something like this. There should be a peak here. And so what Planck did is that he actually just data fit the entire thing. And so from the data fitting, he gained R equals to 2 pi hc squared over lambda to the power 5 e to the power of hc over lambda kt minus 1. So there's some observation here. If you actually just rewrite this, 2c pi over lambda to the power 4, multiply this by hc over lambda, 1 over e to the power of hc over lambda kt minus 1. This is the energy distribution from Maxwell Boltzmann. So this is obtained from statistical thermodynamics, which I won't fully discuss it here. But this Maxwell Boltzmann statistics gives you this average energy for a particular wavelength. So there's something interesting. So from the Maxwell-Boltzmann distribution, what we could get is that the energy in here should be hc over lambda. And this is the same thing as hf. So a very useful thing to know about the Maxwell-Boltzmann equation is that this works for an ideal gas. So does that mean that photons are actually some form of a gas? So we could assume the light as some bundles of particles hitting each other up to the point where it gains its certain energy and its energy distribution. It still makes sense. And so this is where the idea of E equals to NHF comes from. So this is a quantization of energy pretty much, in which you observe that energy could only come within discrete value of the frequency. So Planck thought the idea that maybe light is some form of a particle, but there are also other observations that could actually conclude you to saying that light is particle-like. So here's an experiment. If you have two plates like a capacitor, so there's electric. So there's an electric field going in that direction, yeah. And then you have electrons in here. So if you hit light into this object, there will be some ejection of this electron. So the question is, how much energy does it take for this electron to go to the other side? We could solve this straight away. So the energy must to be half mv squared plus the work from the metal. So this is pretty obvious. And then the energy that requires you to move from one place to the other is Q times E. So the charge of the electron, multiply this by the electric field. So what you could gain from here is that, So there's a minimum energy for this half mv squared to actually reach to the other side, in which it has to be Q times V. So in here, there's pretty much a voltage difference. There's positive, there's negative here. This should be negative, this should be positive. So if there's this QV, which is the minimum value of this half mv squared, you know that the minimum energy for you to eject a electron would be QV plus the W, which means that you could actually get the QV equals to the energy of the would be the energy minus the work. So this is for the minimum value, the boundary condition. So if you think about this, if you know that light's energy depends on its intensity, the idea would be is that there will be a potential. So this is the so this will be the measured voltage so this is the voltage that is placed, or pretty much the one that you could measure, and this is the current. You could observe something like this. So there won't be any current if you apply a certain voltage, but then if you're applying a higher and higher voltage, it will later correspond to a higher energy. So now if you fine-tune your voltage to be at this point where the current is 0, and you change the intensity of light, what ends up happening is that there is this higher band, but it still reaches at 0 at this particular point. So this is high intensity, and this is low intensity. So this observation tells you that the energy doesn't fully depend on the intensity. There has to be something else. And so instead, what researchers do is that they actually compare the voltage to the frequency. Voltage and frequency. And it turns out that the stopping voltage turns out that it has a certain gradient. So we could actually just compute this. V equals to E over Q minus W. And this gradient in here turns out to be H over E, or the charge. So that means that there's something interesting going on. Is that maybe the energy is a function proportional to the frequency, so that it obtains something like this. And it turns out H over Q is a multiplication of F times plus a certain constant, let's say, or minus a certain constant. So this observation tells you one thing. HF is your energy, which further proves the blackbody radiation. So this is what you call as the photon's energy. So the photon always come at the energy of HF for this single bundle of light. But if you have multiple of those, you would have a particular energy. But this gives a certain question. Maybe if you have your electron here, and then you hit it with multiple of these photons, they have the same HF, and so that means that it should have a higher energy. But why couldn't I measure a certain current from it? And the answer really lies on the probability that all of these photons hit this particular electron at the same time. This is the biggest problem. So using only classical theory doesn't give you the full answer, but if you start consider light bundles or photons, you could see this photoelectric effect coming up. And this is what Einstein did to obtain himself a Nobel Prize. So it's a very subtle change of idea, but it changes the way that we think in the quantum scale. So there's a question that normally people ask. What is light? Is light a wave or particle? Wave or particle? And what I will explain later on is that light is both a particle and a wave. And so maybe let's give you another example of light being a particle. So we'll observe the Compton effect. The Compton effect. So the Compton effect will be pretty much if you have light hitting a electron, it will later move at a certain velocity v, and then there is some scattered light that you observe. And this is the angle theta, and this is the angle phi. So if you actually only observe this in terms of the classical way, you would have a wave hitting your electron, and then it will later start to vibrate. And now this vibration will later cause photons to appear because of the accelerating charge. And this emitted photon must be, the emitted wave should be the same frequency as the frequency that it was given. But it turns out that there's a shift. So what you expect from something like this, if you try to measure its intensity, turns out to become something like this for a particular change in your theta. So depending on where you measure your light emitted from the particle, it will have this peak, this double peak. And so this is the frequency from the light, from the incident, and this is the frequency from the scattered. And we want to observe why does this happen. And so this is where we have the idea of this, in which some of the energy is transferred to the electron movement, but there are some energy that is transformed into your scattered light. So let's solve about this. So remember, when you're dealing with physics, you always need to conserve two things, energy and momentum. So let's just do that. Let's try to conserve energy first. So the energy will be HF, which is hc over lambda I, plus the mc squared, which is the energy of your particular particle. And this must be equal to the hc over lambda I, lambda s, which is the scattered light, added by the kinetic energy of your electron, gamma mc squared. So that's the first thing. Second of all, you can take the momentum in the x direction. And let's try to conserve this. So this would be h over lambda I. So that's the one from the incident light. And this would equal to h over lambda s, multiply this by the cosine theta, so this is just the x component, plus the gamma mu, or the relativistic momentum, times the cosine phi. And in the y direction, you could have, so the momentum in the y direction should be 0, which actually concludes that h over lambda s sine theta must be the same as the gamma mu sine phi. So there are multiple ways for you to try to solve this problem, but I think the easiest way to do this is by actually trying to get rid of your phi's, because it's a term in terms of another angle, which contributes to the trigonometry. So let's try to solve this. So h 1 over lambda I. So this is from the second equation. Second and third. This third, this is first. It's lambda I minus 1 over lambda s cosine theta must be equal to gamma mu cosine phi. So you could square 2 squared plus 3 squared, and this is gamma squared m squared u squared. So this would conclude into h squared 1 over gamma I minus cosine theta over gamma s squared plus another h squared sine theta over gamma s lambda s squared must be equal to gamma squared m squared u squared. So you could simplify all of the things by expanding it. So there would be h squared at the front, and then what you have is this 1 over lambda s squared minus 2 cosine theta over lambda s, and then the cosine squared lambda s and the sine squared lambda s, which actually, if you sum them both up, it turns to 1. So we could just write this as 1 over lambda I minus 1 over lambda s squared plus 2 over lambda I lambda s minus 2 cosine theta. This is the same thing, and this is gamma squared m squared u squared. So from equation 1, you could also determine what the gamma and the u is. So what gamma squared is defined was it's 1 over 1 minus u squared over c squared, right? And so we could actually figure out that 1 over gamma squared is 1 minus u squared over c squared. So this would mean that u squared over c squared is 1 minus 1 over gamma squared. So simplifying this much more further, what you could obtain is u squared equals to gamma squared minus 1 over gamma squared c squared. So u squared gamma squared is gamma squared minus 1 c squared. Now from here, going to equation 1, which is this one here, you can simplify everything straight away. Let's try to simplify it first. H over lambda I minus h over lambda s equals to gamma minus I mc. So we could figure out that h over mc, 1 over gamma I minus 1 over lambda s. Sorry, I switched gamma and lambda. So it's that plus 1 equals to gamma. And then if you square off this, you could plug it in, and you would get u squared gamma squared is the same thing as h squared over m squared c squared 1 minus gamma lambda I, wait, yeah, it should be lambda I minus 1 over lambda s squared plus 2h over mc 1 over gamma I minus 1 over gamma s, and everything is multiplied by c squared. So there should be another plus 1, but then because of the plus 1 and the minus 1 cancel each other out, you obtain something like this. So if you plug this into this equation, so I'll call this as 4 and 5. So combining 4 and 5 together, you could see that there's this m squared u squared gamma squared. So we can substitute that value in. H squared over m squared c squared 1 minus lambda I minus 1 over lambda s squared. Oh, okay, so yeah, there's the m squared gonna be canceling each of these things out. Oh, sorry, yeah, there's also c squared there, so it also cancels the front side out. So it's h squared. So it's h squared 1 over lambda I minus 1 over lambda s, everything squared, plus 2hmc 1 over lambda I minus 1 over lambda s, was to equal to h squared 1 over lambda I minus 1 over lambda s squared, plus 2h squared over lambda I lambda s 1 minus cosine theta. I think that is already explicitly written. It's this one here. So from this entire thing, we could see that there are two values which are the same. That means that you could simplify everything as well. You would get mc 1 over lambda I minus 1 over lambda s was to equal to h over lambda I lambda s 1 minus cosine theta. So this would later, so if you multiply everything by lambda I and lambda s and dividing it by mc, you would get lambda s minus lambda I, which you will call this as delta lambda, or the Compton shift, and this is equal to h over mc 1 minus cosine theta. And this is what you call as the Compton shift. So this is the shift in the wavelength when you hit a charged particle with a photon, and it will scatter some of the light. So this observation tells you one thing, is that actually the momentum was energy over c, and you know the energy of a photon to be h F over c. So we could conclude that it's h over lambda is also your momentum. This is a very interesting fact to keep in mind, because this is something that I also used, but I didn't explicitly say so. So let's talk about the atomic spectra and also the Bohr atom. So let's think of the hydrogen spectrum. So the hydrogen spectrum, if you have, so we will just use the model that they used for this entire derivation, in which hydrogen has one proton and one electron. And so a simple theory of this is that it's orbiting. So the electron is orbiting the proton, and there are certain things that needs to be thought of. First, electron whizzing around the proton corresponds to acceleration. And from classical electromagnetics, a accelerating charge particle needs to lose energy in the form of light energy. So this means that this model is wrong. Somehow it's wrong. But there is no models that has explained this before. So now we will discuss about the Bohr's atom. But before we go to the Bohr's atom, we need to talk about the hydrogen spectrum. So if you shine light, so I will denote this as HF, hitting your atom, it turns out that it would absorb some of the energy of the light. And so this is why, if you actually look at the atomic spectra for the hydrogen spectrum, there are these black lines, which corresponds to the frequency that this hydrogen is absorbing. So people have been trying to study how do you get these black lines at, and one of them is the Balmer series. And so the Balmer series says that 1 over lambda is RH 1 over 2 squared minus 1 over n squared. So this is one type of the series in which a particular frequency will later be absorbed. That's why you have the black lines. And this RH in here actually corresponds to 1.0968 times 10 to the power 7 per meter. This is a unit that they discovered from experiment or from data fitting. And also this n here actually corresponds to values greater than t as long as it's an element of the real number, greater than equal. So 3, 4, 5, 6 of them works. And it turns out that this could be generalized much more further. It's actually 1 over lambda equals to RH of 1 over n2 squared minus 1 over n1 squared, in which n2 must be smaller than n1. So if you observe this from the quantum mechanic perspective, 1 over lambda is actually momentum. But you could also observe that it's actually some form of energy. So the energy would be Hc RH 1 over n2 squared minus 1 over n1 squared. And this observation gives you another clue. The energy of a particular value, so let's say En, is actually negative Hc RH 1 over n1 squared. And this, in theory, should be 13.6 electron volts from observations as well. And so this is what Bohr tried to explain. So the Bohr model gives you a simple clue. So what Bohr did was he realized that H has units of its joules second. So H is joules second, and this actually corresponds to a unit of kilogram meter squared per second. And you could rearrange this into a much more noticeable form. It's meter times kilogram meter per second. This is momentum, and this is distance, L. Length, or R. And this is actually proportional to the unit of angular momentum, L. So what Bohr did was that he thought that maybe H is maybe you could actually compare H with the angular momentum. And maybe that's where the energy is quantized at, because you could see here the energy is quantized as long as n is a natural number, which is quantization. So Bohr tries to do that. He thinks that, okay, MVR, that's your angular momentum, must to be some multiple of H. And this multiple here, I'll call that as the function of n. I don't know what function of n is, but for a particular value of n, it will later correspond to a particular energy. So by combining this with the standard classical model, what you could get is that the force must be mv squared over r, and this must equal to the electrostatic force, which is q squared over 4 pi epsilon 0 r squared, or kq squared. So in here, I'll just be using k, or the electrostatic coefficient. So this would later resolve into mv squared r equals to kq squared. So the realization that this mv squared r is actually this. We could actually write this L, so this is angular momentum. So it's the same thing as the angular momentum over mr equals to kq squared. So you could figure out what the r is only from this entire equation. The radius of the atom would be L squared over mkq squared. So now, observing from the conservation of energy, E must equal to half mv squared minus q squared over kq squared over r. So this is the electrostatic potential energy. And the half mv squared corresponds to the electron whizzing around. So you could plug in what the v squared in here is. So actually mv squared is actually kq squared over r. So this is actually negative kq squared over r, which also corresponds to the, it's negative kq squared over 2r. Or if you actually substitute this with the L squared, this is negative k squared q to the power 4 over 2L squared. Sorry, at the top there should be another mass. So this is the energy. But remember what L is. The assumption was L is h multiplied by a certain function n. So maybe we could substitute this in mk squared q to the power 4 over 2 the L squared, that's h squared function n squared. Now this must be the same thing as the negative 13.6 over n squared. Now this gives a clue. Maybe function n is actually proportional to n. So if you substitute this into, let's say, a times n, you could solve what the a is, because you know all of the other values. And it turns out that this a is actually 1 over 2 pi. And this is one of the elegant things, is that actually the function n is actually n over 2 pi, which means that your angular momentum must to be n h bar. This is the quantization that Bohr made, which makes it possible for you to construct all of the series, like the Balmer series, Paschen series, or the Lyman series, so that it is able to form based on solely on this model. So we could simplify everything altogether, as now we know what the value is. So we could know what is the smallest atomic radius only from this equation. So if you put the L here to be nh bar, when n equals to 1, you would have h bar squared over mkq squared. And this is about 0.0529 picometer. And this is the radius of the hydrogen. Oh, sorry, not picometer, but nanometer. And also, only from getting this A0, you could substitute this into this energy, which is actually a negative mk squared q to the power 4 over 2h bar squared n squared. So we could simplify everything so that we could get En to be negative ke squared over 2a0 1 over n squared. And this value is 13.6 electron volts, exactly what we found from experimental data. So this idea actually could be extended towards the idea of ionization. So when n goes to infinity, or if it has a very large angular momentum, this will later evolve into where En would be 0. So this means that your electron goes out of the effects of the atom. And if you actually compare this to the original state of the energy, you could figure out what's the energy needed to remove this one electron. And this is the core when you're dealing with chemistry, so that the electron needs to be taken off for you to form electrostatic bond or covalent bonds, in which it is mostly discussed in terms of the wave function instead. But this model, Bohr's model, couldn't truly describe every single atom. If you have something like helium has a 2 plus and nucleus, and no, sorry. So the nucleus has 2 protons and 2 neutrons, and then there are 2 electrons whizzing around. Unfortunately, if you are actually using Bohr's model, this actually turns out to be actually needing to have another electrostatic force between the 2 electrons. So the Bohr's model only works if you're talking about single electron systems. So I want to start to talk the discussion about matter waves. So what Planck did was he was able to figure out that light behaves like a particle. But there's another person, which we call him as the Broglie. He theorized that maybe matter is also wave. So let's think about this. Hc over lambda is your energy, which means h over lambda is your momentum. But let's just assume if you have your matter to have a certain momentum, it pretty much corresponds for it to have a certain wavelength, to have a certain energy. And this is exactly what we call as the de Broglie wavelength. So this is what de Broglie did, and he realizes why there is quantization in the angular momentum. So if you have this proton and the electron whizzing around, it's spinning around at about the length of 2 pi r, which is the circumference of the orbit. So if we assume that the electron is a wave, we could just assume it's something like this. So there's one condition in which this and this must be continuous. And also its first derivative should also be continuous. So this would be just a traveling wave as long as it's periodic. And so the condition of this is 2 pi r, which must equals to n lambda. So the wavelength, and then you could have a higher wavelength. You could have a smaller wavelength that also corresponds to this, as long as it's periodic by nature. And so if you actually substitute this with the lambda equals to h over p, you could get nh over p. And p is mv, momentum. So mvr is nh over 2 pi. And this is nh bar. So what Bohr's model did was that was that he was like thinking maybe there's something to do with the n, and he figured that the value was it was h bar times n. But what the Broglie did was that he was able to figure out that if you assume that the electron is a wave, this quantization of angular momentum already exists from the definition if you know the Broglie wavelength. So because of this idea of matter also becoming waves, maybe particles could also behave as if they have interference or diffraction. And it turns out that that is the case. And so this is where, when you do the double slit experiment, but instead of light, you could do it for particles, it ends up becoming a diffraction pattern. So what you expected was there should be a buildup of electrons, but it turns out that it's not. There's this interference pattern for even matter. So this is where I will go into the uncertainty principle. So the uncertainty principle tells you of certain things. You couldn't measure anything very precisely. There's a limit of this. And so from the book, it is defined to be delta x times delta p is greater or equal to h bar. But what I normally study is that I take this of h bar over 2, because what h bar over 2 tells you is that these are pretty much standard deviations. But if you're doing it with h bar, it means that the deviations doesn't really mean it's standard deviation. So I will just note this down first. You couldn't measure anything very precisely. And let me show you why. If, let's say, you have a charged particle moving, and then you want to look at it, the only way for you to look at it is if the electron itself is emitting energy, or photon. But if this electron is emitting energy, this means that its momentum changes. And so if you try to measure its position, you end up changing its momentum. So that's why you have this type of relation. Same idea if you say trying to measure matter, like an electron, whizzing through a very small slit. If it has some deviations, it might have this repulsion or attraction with the wall, which actually causes this diffraction. So in the end, you couldn't really determine if you're measuring something very precisely. You could only do it until a certain order. And this is also true when you're talking about the energy as well as time. So if you try to measure the energy of a certain particle at a particular time, well, you know the particle would have a certain energy, but you don't know at which time period. And same thing, if you figure out where the particle is at a certain time period, you don't know its energy. That's a very interesting discussion to talk about. So, after we have discussed about the idea of the uncertainty principle, I will discuss about what exactly is the principle of complementary. So, complementarity tells you that your object is both a wave and particle. They are pretty much the same side of the coin. They are different sides of the coin, but they correspond to the same physical system. But there's also another property, which you call as the correspondence principle. And this pretty much tells you that if you are trying to measure, let's say, light, if it is a wave, the effect is that the result that you would have is that your particle would be a wave. But if you're measuring your system by assuming that it's a particle, you would observe that the system will turn out to be something like a particle. So that's all about quantum theory, in which we start to discuss about the idea of quantization of particles and waves, and then we try to interpret what does it exactly mean. But going forward, so the next chapter will be involving quantum mechanics, in which we discuss what exactly quantum theory is and what's the mathematics behind quantum theory. So this is a much more generalized form of quantum theory. But that's all for today, so thank you very much for watching. So make sure to like and subscribe, and also please share this to your friends who really needs to understand physics in a much more deeper understanding. So thank you very much, and I will see you on the next video.